Let me take my face out of the recording. I'm camera shy. Shall we start? All right, let's do it. Problem one. Oh, I had this a second ago. All right, get in the outline. Okay. You have to deliver crucial supplies using airplanes with unreliable engines. Each engine has a probability P of lasting for the entire flight. Okay. What am I writing with? I'm writing with a highlighter. Oh my God. Okay. Each engine has probability P of surviving. Engine failures are independent. Half or more of the engines fail, the plane crashes. Our choice between using a 2-engine plane, which will crash if either engine fails, or 4-engine plane, which will crash if 2 or more engines fail. Okay. Plane crashes if more than half of its engines fail. Okay. Part A. What is the probability that exactly 3 engines on a 4-engine plane will survive? Thoughts?
D binomial, 3 out of 4 with each probability of each.
Yeah. So in other words, we can think of each engine as a Bernoulli random variable. Okay. So say that we have, and this is just generalizing, but say that we have a binomial random variable with n trials and probability P of success. And what's its mass function?
And choose X.
Okay.
Probability
P to the K.
Yeah.
N minus X.
Okay, so in other words, in every single one of these configurations has probability P to the X times 1 minus P to the N minus X. And then we just count the number of configurations. And we have something that's going to look like, well, let's see, so we have 4-engine plane, 3 are going to survive, and 1 is going to fail. Okay. So say that we survive with probability P, that's a success, and we fail. You can call it Q if you want, but let's just call it 1 minus P. That'll come in handy in a little bit. So with that in mind, what's our probability? Somebody might have said it earlier, but can somebody repeat it? Okay. So what people have in the chat is right. So 4 choose 3 times P to the 3rd times 1 minus P. Or this is the probability that 3 survive, 1 fails. This is the number of configurations. And the probability is multiplied by independence. Since engines survive, I can't spell. Survive and fail Everybody okay with that?
Yeah.
Okay. Part B. Determine with what value of P the probability that a plane will not crash is the same for a 2-engine and a 4-engine plane. Okay. So first of all, what has to happen for a 2-engine plane not to crash?
None of the engines fail.
Yep. So in other words, this is the probability that all of its engines survive. Okay, and what's that probability? Why is it 1/4? So what's the probability that one engine survives?
P, so it's P squared.
P squared, yeah. Each survives a probability P, and the events are independent. Okay. So the 4-engine plane is a little bit more interesting. So when does a 4-engine plane survive?
At least 3 out of the 4 engines survive.
Yeah. So 4-engine plane survives. It's the same thing as the probability that greater than or equal to 3 engines survive. And depending on how technically you want to be here, you can say there are 2 events here, of which we're taking a disjoint union. This is the probability that 3 engines survive, that's one event, unioned with the event that 4 engines survive. These events are disjoint. So this is the probability that, so by finite additivity, this is the probability that 3 engines survive. Oops. Plus the probability that 4 engines survive. And now we just have to work out these little probabilities. This isn't too bad. So let's start with the 3-engine, with the probability that 3 engines survive. I think we did this earlier, didn't we?
Yeah.
This one we can just get. Yeah. So this is 4 choose 3, P to the 3rd times 1 minus P. Okay, and the probability that 4 engines survive?
P to the power 4.
Yeah. And yes, to Ken's question, yes, that's just union. It's union, but basically it means or. All I'm saying here is that you can think of this as a union of 2 disjoint events. Okay. And you want to write this more compactly. 4 choose 3 is 4. So this is 4 P cubed times 1 minus P plus P to the 4th. Okay. And what's Paul trying to get us to get? Determine for what value of P the probability that a plane will not crash is the same for 2-engine and 4-engine planes. So what do we do?
This equal to P square and solve for P.
Yeah. So P squared is 4P cubed times 1 minus P plus P to the 4th. Okay. And so the first thing we're going to do is say, if P is 0, this thing is just trivially going to be equal. So certainly we have equality if P equals 0. That's not a very interesting case. And the reason I'm getting rid of that right now is I want to divide through by P. Now we're going to consider the case where P is not 0. So multiply this out. So p squared is 4p cubed minus 4p to the fourth plus p to the fourth. Let's see, let's divide through by p squared. I'm totally going to make an arithmetic error at least some point tonight, but we'll see. This is going to be 4p minus, let's see, 4p squared plus p squared. Oh, so far so good. Why does this look wrong to me? What did I do? Ah, okay. This is fine, actually. Let's see. So I'll yes, so we'll combine these two terms. Negative 3p squared plus 4p. Is that right? I guess so.
Yeah.
Okay. And now we'll do some factoring. What does this factor into? Well, if you want to do this the way you learned back in Algebra 1, 1 or a third is right. Yeah, so we can say this is negative 3p squared plus 3p plus p plus 1. And then we take out a factor of 3p. Plus, did I just do that? This is not going to work out.
Why don't we multiply by -1?
Yeah, but that'll certainly make our life easier. Okay, so now this is going to be 3p squared minus 3p minus p plus 1. Now we can do what we were just doing. This will be 3p, p minus 1, minus p minus 1. There we go. Take out a factor of p minus 1. Okay, now we solve. So p minus 1 implies that p is 1. That's rather silly. Of course, they're going to be equal if all the engines survive. Well, 3p minus 1 is 0, which implies that p is 1/3. So in other words, our solution is p is 0, 1, and 1/3. So the two trivial cases and 1/3. Sound good?
Yes.
Okay. Part C. Would this value of p would 6 engine planes be a better choice? Okay, so the reason that Paul is referring to a single value of p here is because he's saying throw out the trivial cases, only consider the non-trivial case. So what we're going to do is we're only going to consider p equals 1/3. We only consider case p equals 1/3. And JS's answer is correct, but we'll work this out. This value of p with 6 engine planes be a better choice? Yeah, so all we really have to do here is plug in, right? So let's do that. But we're interested in 6 engine planes surviving, okay. And we didn't work that out, did we? No, we didn't.
No.
Okay, so we'll work that out first. So when does a 6 engine plane survive?
3 or more engines survive.
Did you say 3 or more?
Yes.
So if 3 survive, then that means that 3 fail.
Oh, okay, 4 or more.
4 or more, yeah.
Yes. Okay.
3 engine plane survives. So that's the probability.
4 or 5 or 6.
Yeah. So I'm going to write it more directly this time, since we already sort of did the formalization. 4 engines survive. That's the probability. 5 engines survive. Oh my goodness. I'm going to run out of space. I'm going to scroll to the right and then do the math below. Thank God for OneNote scroll. It's kind of funny. I was presenting a proof yesterday to somebody because I'm a nerd. And I thought that I actually had ran out of space on OneNote, which supposedly has infinite scroll. That's how ridiculously verbose I am. Okay. Okay, 4 engines survive on a 6 engine plane. That's a probability. And all we're really doing here is we're considering every single time we change the number of engines in a plane, we're considering a new binomial random variable. Probability is the same, but the number of trials changes. In this case, our number of trials is 6. In other words, you can think of this as a binomial random variable with 6 trials and probability p. For the moment, this is just an arbitrary p, but we're going to plug in 1/3 later on.
E to the 6th power.
So that'd be 6 engines surviving.
Yes.
Okay, sure.
Plus 6p to the 3rd power times 1 minus p to the 3rd power.
Sorry. 6p to the 3rd power?
Yep.
Okay.
Times 1 minus p to the 3rd power. And then 15p to the 4th, 1 minus p squared.
Okay, so just 1 second. So 6p to the 3rd, what does that correspond to?
That is the amount of successes or that the engine will survive.
So in this case, 6p to the 3rd, so that would imply that 3 survive, right?
Yes.
Well, if 3 survive, though, the plane crashes.
I see. Okay.
So p to the 6 is indeed the probability that 6 engines survive.
Should be 6p
So p to the
5th.
5th and then 1 minus p to the 1st.
Right.
Sorry.
Minus p to the 1st. Okay, and how many of those are there?
6.
Yeah.
6 choose 1. 6 choose 5.
6 choose 1, 6 choose 5, same thing.
Hmm.
Yeah. And 4 engines?
6 choose 4, and then p to the power 4, and 1 minus p to the power 2.
Mm-hmm. And now all we have to do is plug in. I'll be totally honest. I plugged this in with R myself. My notes have R code. That's how bad I am at pencil and paper arithmetic. So I think somebody worked this out already, right? Okay, JS's numbers are correct. So if we plug in for 6 engine plane, we get 0.10013. Oh, he has more decimal places than me. I got 1372. Let's go with JS's number. 717. JS, did you use Python or a calculator? Because if you use Python, Alec will be very happy. Oh, you used R. Mm-hmm. Okay. You must have it set to give more digits than me. I was gonna say, if you used Python and you got 1 more digit of precision, Alec would be very happy. Oh my goodness. So 4-engine plane, 0.1111, blah, 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 a bunch of ones. So what's the conclusion? Is the 6-engine plane better? Off in Java, okay. Nope, it is most certainly not better. Nope. It's nope, the 6-engine isn't better. The 6-engine is not better. Okay, it wasn't too bad. Problem 2. Yeah. Yeah, JS's point is well taken here. Most certainly what we're going to do is we're going to handle the really trivial case first. Well, it's not trivial, but the easiest case. And then we'll get into the more complicated ones. Okay, let's see. Each contribution to the Harvard College Fund brings a reward by email, a photograph of Lawrence Bachow, Derek Bach, or Drew Faust. The probability of getting a Faust photo is 1/2. Well, the probability of getting a Bachow or a Bach is 1/4. Okay, 1 second. Oops. Probability getting Faust is 1/2. Probability of getting a Bachow or a Bach is 1/4. An alumnus vows to make contributions until he has a complete set of photos. The number of contributions required is a random variable y, sum of geometric random variables. Y is the number of contributions needed to get all 3. Use what you know about the expectation of a geometric random variable. Show the expected number of contributions to get a complete set is 19/3. Okay. And the comment in the chat is a very, very good one. I think to motivate this, we should draw a tree. Most certainly is not required, but give us an idea of what's actually going on here. Does anybody want to veto the tree? Veto the tree won't do it. Okay, let's see. So we start. Yeah, certainly. We can do either of them. My goodness, my email right now is exploding. That's okay. I'll get it later. I misspelled Bachow. Oh my goodness. Yeah, if you misspell the name of a Harvard president, you get fired, is what I heard. So I think I'm in trouble. Okay. So we can start at a Faust and get either a Bachow or a Bach, and then we get a Bach or a Bachow. If we can start with a Bachow and then get a Faust or a Bach. And similarly,
First, not backward, last one. Previous one.
Right. Oops. Oh, I didn't draw this too big. This is Bachow. This is Bacco. This is Faust. Okay. So first things first. What's the probability that we get a Faust first?
1/2.
Yeah. And probably that we get a Bacco.
1/4.
1/4. And a Bach.
Same 1/4.
Yeah. So these are unconditional probabilities. So let's deal with the Faust branch first. Right, so there are two possible configurations in total, right? We could either go Faust Bacco Bach or Faust Bach Bacco. But each of these are exactly symmetric, right? Because Bacco and Bach are equally likely. So in other words, we don't need to condition on the second photo. Does that make sense to everybody?
Yes.
Okay. So if we condition on getting a Faust first, we can say the expectation, let's call it X for the moment. The expectation of X, let's call it X1. The expectation of X1, given that we get Faust first. So by assumption, we drew a Faust first. Our first photo is going to be a 1. Or rather, we first drew a Faust, so it's only going to take us 1 draw to get the Faust, right? And then after we drew a Faust, what's our probability of success? Or I should say, what is a success after we've already drawn a Faust?
Bacco or Bach?
Right. And what's the probability of getting a Bacco or a Bach?
Half.
Half, exactly. And maybe for motivation, I'll write that as 1/4 plus 1/4. So our new probability of success is 1/2. So how many trials do we expect in order to get one of those?
2.
Yeah. So in other words, 1/p, right? As one. So if we have a geometric random variable x with probability of success p, its expectation is 1/p. So our new probability of success is 1/2. We're going to expect 1/1/4 plus 1/4. So this is, we get a Faust. Here we get a Bacco or a Bach. And again, because these cases are exactly symmetric, we don't need to condition, right? So the only thing we really are interested in now is getting a third photo, getting whichever one is left. So what's the probability that we get that third one, whichever it is?
1/4.
1/4. And if we do this out, we get 1/1/2 is 2. Sorry, this is 1/1/4.
Yeah.
Yeah. I was thinking that looks weird. So 7. Okay. So if we get a Faust first, we expect it'll take us 7 photos to get the other 2. Sound good?
Yeah.
Okay, so we dealt with the first branch. This is all set. So this is a point that JS was making earlier. So the Bacco and the Bach case are exactly symmetric, right? If we were to work one of the cases out, literally all we would have to do is interchange the labels Bacco and Bach. We would get precisely the same numbers.
Mm-hmm.
What we can do is we can work one of these cases out and then multiply by 2.
Sure.
To save ourselves some time. So we'll say by symmetry, expectation of x2 given Bakau is expectation of x3 given Bach. So we will work out 1 and multiply by 2. Okay, so should we do Bach or Bakau? I have to admit, I'm inclined to do Bakau only because I mispronounced the name, or I misspelled the name earlier, and I feel like I'm kind of on shaky ground. Okay, fair enough. So we'll do Bakau a second. Okay. Okay, so consider Bakau second. Thinking of bacon. Oh, now I need to go eat some bacon after this. Okay, so really there are only 2 possible configurations. 2 possible configurations. And they are Bach, Bakau. Sorry, these are flipped. Bakau, Bach, Faust, Bakau, Faust, and Bach. Okay. So we'll set up our expectation using basically the exact same logic as before, but though there's an additional twist here. The expectation given Bakau first. Oh, again, how many photos will it take us to get a Bakau?
1.
1, right? Yeah, that's our assumption. So get a Bakau. Okay, and from this point, what's our probability of success?
3/4.
Yeah, so in other words, 1/2 plus a quarter, right?
Yeah.
You'll write that 1 over.
Yeah.
Yeah.
Let me write this one down. 1 over 1/2 plus a quarter. And at this point, we're in sort of a bit of a pickle that we'll have to get out of, which is, what's the probability of success for the third photo? It depends, right?
Mm-hmm.
So in other words, we have to break this into 2 different cases by conditioning on the second one. So this is really for illustration, so we can say plus, it depends. Okay, so let's go with the first case of Bakau, then Bach, then Faust. So let's say expectation of x squared given Bakau. Did I say do Faust second? Yeah. Let's do Faust second. So the first 2 numbers are precisely the same as before. This is 1 plus. This is get Bakau. The second we have a success. I misspelled the name again. Oh my goodness. I am getting fired. Oh, I misspelled it above too. Oh no! Wait, no, I didn't. No, it is a C, isn't it?
It's a C.
It's a C. Okay. Oh my god. Yeah. I'm getting fired. Okay. So success in the second case just means get one of the other 2. So it's going to be get a Faust or a Bach. Right. But based on our condition, we got a Faust. But we know we got a Faust. Okay, so in other words, for our third photo, what's the probability of success? Or what is a success?
1 over 1 by 4.
Yeah, so in other words, we have to get the Bach photo. In this case, we have to get Bach.
So I have a quick question. If you are saying that second is forced, then should we not just be doing 1/1/2, like saying that that's what we are going for? In the second branch, it will be the other way, 1/1/4, because the choice of the two is not our second situation.
So the idea here is, no matter what, after we get a FOST, it will be successful if we get either of the two.
Mm-hmm.
The only time it factors in which one we chose second is one in the amount of trials it takes to get the third, and eventually in the conditional probability of these two cases.
Okay.
Yeah, so in other words, we're going to account for that in a little bit.
Okay. Great.
So let's see. So this is 1 plus 1/3 plus 1/1/4, which is 1 plus 4/3 plus 4. Watch me fail at arithmetic. It's going to be 3 plus 4 plus 12/3, which is 19/3. It's not the final answer, but it looks like it looks like we're in the ballpark. That's our second case. So let me just go back through this. So we did FOST second. So we handled this branch right here. Now we have to deal with this branch right here. Bach-Al, then Bach, then FOST. So perhaps a better way to answer your last question is the second condition comes into play after we have already gotten at least one of these and we're branching out.
Okay. I see.
Okay, so let's see. So now it's expectation of x2 given Bach-Al first, then Bach. Okay, so first, once again, it takes us 1 to get the Bach-Al. Plus 1/, we already said this is 1/3.
Mm-hmm.
We get a FOST or a Bach, but we know we got a Bach. But we know we got a Bach, and then plus, so now we have to get a FOST. So what's the probability of getting a FOST?
Half.
Sorry?
Half.
Right, half. Yes, that's 1/2. Okay. So therefore, we get 1 plus 4/3 plus 2, which is 3 plus 4 plus 6/3, which is 13/3. Okay.
Wait, I have a similar question to the previous question that was asked.
Yeah.
How come when we assume Bach-Al first, we just assume that it took one photo, but then for the other one, we factored in the probability?
Right. Yeah. So I think that'll probably be clear after the next step. Basically, what we're about to do is we're about to get the conditional expectation of x2 given Bach-Al first. We have to condition on getting Bach and getting FOST. If we were to do that in the case of getting FOST first, our two conditional probabilities would be 1/2 each. In other words, we'd be equally weighting two identical cases.
Okay.
So in effect, what we're doing is saying, because these two cases are symmetric, we're saying, okay, we got a FOST first, without loss of generality, suppose we got a Bach-Al first, and then we got a Bach. And by symmetry, these are exactly identical cases.
Mm-hmm.
Good question. So what we're gonna do now is, I don't know if Paul formally gave this in lecture, but let's introduce it. So how many of you have heard of the law of conditional expectation? So I'll put you on the spot then. What is the crux of the law of conditional expectation? Sorry, law of total expectation. Very, very similar to LTP, yes. Yeah, it's the expectation variant of LTP. So if I were to write this in maybe kind of a non-formal way, law of total expectation. So we can write the expectation of some random variable x. Maybe I shouldn't call it x, but we've been using a lot of x's. So with apologies to another Prof ITA4 who insists that we only use z for standard normal random variables, I'm going to call it z. So, and this is discrete. Discrete. This means that we can get the expectation of z by summing over cases of the expectation of z given case, say I, times the probability of case I. And formally, we can say we have a set of events that partition the sample space. And if we were to sum up the conditional expectations over all of those cases and weight them by the probability of the case, we get the expectation of the random variable. Does that make sense to everybody? So we can write an expectation as a probability weighted average. This is true for any partition.
So remind us, what was the weight? What acts as the weight?
Yes. So the weight here, in the general case or in the specific case that we were doing?
In the general, please.
Right. So that's the unconditional probability of case one. Okay, how about I give you an example? So say that we have two cases that partition the sample space. So I don't know. Case one is, I don't know, it's raining. Is it raining right now? Probably not. Case two is it's not raining. Maybe this is the event A. This is the event A complement. Clearly these partition because A union A complement, they're disjoint and their union is the entire sample space. Say that the probability of A is, I don't know, 0.8. Probability of A complement is 0.2. So the expectation of some random variable z would be the expectation of z given A occurs times the probability of A plus the expectation of z given A complement times the probability of A complement. That works for any partition.
Okay.
Is everybody okay with this?
Can you scroll down just a little bit again?
Yeah, sure. It seems like this example actually helped. It's good. As we're going to go, really? That's the example you came up with? Is it okay if I go on?
Yes.
Okay. So what we're trying to get right now is, and there's a really messy formula for extra conditioning. So I think I will omit that additional formality for the moment. So let's see. So with the expectation of, what did I call it? X2. Okay, X2. Given Bakau first. And really what we're doing is we already have a conditional expectation and we're conditioning on an additional event where the additional partition is we got a FOSS second or a Bach second. Okay. So in other words, we have the expectation of x squared given Bakau first and Bach second times the probability of Bach second and Bakau first. Technically, I wrote that incorrectly. Let's see. Let's just write Bach second. Technically, it'd be Bach second given Bakau first. Is that right? Yes, that's right. Okay.
Similarly for expected also.
Right. Yeah. All we're doing here is switching the labels. And my apologies if my writing is illegible. Here's the probability. Lost second given Bakau first. Okay. And there are a lot of different ways to think about this. So the first thing that you can say is the probability of getting a FOST is twice as large as the probability of getting a Bach, right? Probability of getting FOST is twice as large as getting Bach. And these two events partition, so the probabilities have to sum to 1, correct? So in other words, the probability of Bach second given Bakau first plus the probability of FOSS second given Bakau first have to sum to 1, correct? Mm-hmm. Okay. So in other words, we can write, let's see, so let's let X be the probability of getting Bach second given that we got Bakau first. So we have X plus 2X is equal to 1, right? So X is the probability that we got Bach second given Bakau first. 2X is the probability that we got FOSS second given Bakau first. Everyone okay with that?
No. First of all, they are independent. So how does it matter Baku first given, Box second?
Oh, these events are actually not dependent because they're disjoint. If one happens, the other one surely didn't happen.
Mm-hmm.
Okay, so in other words, these probabilities have to sum to 1 because they partition the space. Or they partition. We're sort of considering like a separate sample space,
I see.
conditioning on having gotten Bacow first. So this implies 3x is equal to 1, in which case x is 1/3. It sort of makes sense, right? We're thinking which is more likely. Well, Faust is twice as likely as Bacow, so the weight should be 2/3 on Faust and 1/3. I said that incorrectly. So the probability of getting a Faust is twice as large as the probability of getting a Bach. So the probability of a Bach should be 1/3. The probability of a Faust should be 2/3. Everybody okay with that?
That sounds okay.
Okay. So in other words, this probability of Bach second given Bacow first is 1/3. And the probability of Faust second given Bacow first is 2x, which is 2/3. Okay. With that, we can actually get the conditional expectation of x2 given Bacow first. I'm trying to think of where to put it. Okay, let's see. I'll scroll down. So the expectation of x2 given Bacow first. Okay, so first let's consider the Faust second case. How many did we expect it would take if we had Faust second? So in other words, we had Bacow.
It was 19/3.
Right? And that has a weight 2/3. And how about the second case, which is Bacow?
19/3. Not 19/2.
Oh, sorry. Right. Okay, and then the Bacow Bach Faust case?
13/3.
Right. The weight of 1/3. Okay. So then we compute this. This is 38 ninths plus 13 ninths, which is 51 ninths, which will simplify to 17/3. And believe it or not, we're basically done. We just have to put all of this together. Okay, so now we're going to use our law of total expectation formula once again. So the expectation of y, that was the number of contributions needed to get all three. So this is a sum over cases of the expectation of y given cases times the probability of those cases. So the first case was Faust first, right? So we expected that it would take us 7 trials and that had a probability of 1/2, right? And then our second case was Bacow first, right? That has, after conditioning on the second, that took 17/3. And what's the probability that we got Bacow first?
1/4, 1/4.
Yep. And then we could add an additional case, Bach first, but all we have to do is multiply this by 2 by symmetry.
Mm-hmm.
And if we did this right, this should come out to 19/3. This is 7/2 plus 34/12, which is, let's see, 21/6 plus 17/6, which is 38 over 6, which is 19 over 3. Thoughts? I mean, it's like magic, right?
Sorry, I have a quick question.
Yeah.
Why couldn't we just calculate expectations at each node of the tree and then just multiply through the probabilities?
Sure.
It's just the binomial tree that I attached to, in the chat. Essentially, then it saves you a lot of time, like of not going through like all these messy calculations, because then everything just cancels out.
So by summing over the nodes, you mean the final nodes, right? So in other words,
no, like through the nodes. It's like I don't know if it's okay if I share the screen, because it will make more sense.
Sure, go ahead. Okay, 1 second. Let me unshare. I have this on my iPad. 1 second. Stop sharing. Okay. Okay, go ahead.
Yep. So the idea was that here you can say that, okay, at the first step you'll definitely get one of the pictures, like either one, right? So then you say that if the first picture was false, then the second, in order to get one of the other two pictures, your expectation is 4 over 2, right? So it's 1 over 1 over 2. And then because by default it's not going to be false because you got it in the first round, so then expectation is of getting the last missing picture is going to be 4 over 1. So far so good. And then you can do the same thing where if the first picture was not false, then you say that you have 4/3 expectation of getting one of the missing pictures. And if it was false, then you have 4 over 1 expectation. If it was not false, then then the expectation is 2 over 1. And essentially, you just make sure that these probabilities sum up to 1.
Right.
And you just multiply through all these guys, and they just like neatly cancel out, and you get. Like, is there anything wrong? Like, my question is like, is there anything wrong with my reasoning?
No, there's absolutely nothing wrong with that, and that's actually a very efficient way to do it.
Okay, cool.
Yeah.
All right. Thanks.
Absolutely.
How do I stop sharing now?
The green button at the bottom.
Yeah. Okay. Gotcha.
Yep. Yeah. Right. Very nice solution. And if anybody wants to use that, they should cite him as a collaborator. I feel like everybody is going to put that together now instead of my long solution. To maybe save people some writing. Let's see. Okay, problem 3. Okay. What is problem 3? Craps. Like the game craps. That wasn't an outburst on my part. Yeah. Which one? Do we need to show working as to how we know how much one will gain given what is rolled? Yes. Yeah. That's a big part of it, right? And we'll find an efficient way to do it. This is what I actually do have an efficient solution for. I know it's rare. You placed a $495 bet on Nathan Detroit to win at the craps game. The intention of selling off our position, blah, 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 blah. So the outcome of first roll is a random variable X with 5 possible values. Okay, so our 5 values correspond to our 5 cases. All special cases were worked out in lecture. Show that the expected value of X is 488. Okay. So we bet 495. X is outcome of the first roll. And we want to show that the expectation of X is 488. So I can't think of a better way to do this than to write a table. How do people feel about that? JS, as usual, is way ahead of us. Okay. Okay. Yeah, I mean, it's basically the same thing, except same thing. I mean, one of them involves a nice tabular display in tech, and one doesn't. Okay, so let's see. Considering our first roll, probability of that roll. Yeah. Yeah. Did I write 496? No. Okay. Then the payoff. Okay. So Paul pretty much gives us the cases. Okay, so we have two trivial cases. What are those trivial cases? By trivial, I mean whether we just win or lose. When do we lose at craps?
Can you get a 7?
So 7 or 11, we win. So let's do that maybe. So 7 or 11. So if we get a 7 or 11, we win and we double our bet, right? So what's our payoff?
$990.
Yeah. Oh, it's 495 times 2 or 990. Okay, so that's one case. We have 5 of these. What happens if we get a 2, a 3, or a 12? And I'm going to put the probabilities in later. JS is writing this out all nicely in the chat. If anybody wants to take a look at what he has to verify their work. So what's our payout if we get a 2, 3, or 12?
0.
0. Okay. Okay. So from here we have 3 more cases. So we get a 5 or a 9, a 6 or an 8, or a 4 or a 10. Okay. So let's actually, you know what? Oh. Okay. So somebody give me the payoff for one of these cases. And you can pick whichever one. Stupid scroll. Oh my goodness, I need to be careful with this. Okay.
For 5 or 9, the payoff is, I'm guessing, 4/5 times 495.
Yeah. Yeah, so yeah, that's right. 4/5 times 495. And that comes out to 396.
Yep.
Okay. Okay. Anyone have another case?
For 6 or 8, our payoff is 10/11 times 495.
Okay. Good. And was that come out to?
Um,
450, it seems.
Sorry?
450, is it?
450, right. Okay. And then finally forward 10.
so that's 2/3 times 990.
Or 2/3, so close. So 2/3 per dollar, and we bet 495. So in other words, for every $3 we bet, we get back 2.
Okay, so 2/3 times 495. So that's
Yeah.
That's 330.
Right. Okay. So we kind of save these probabilities for last. So what's the probability of rolling a 2 or 3 or a 12? And depending on how long people take to get these, I might draw out a picture. You don't have to do the picture. It's not the only way to do it, certainly. So different color.
1/9.
1/9, right? Running in a highlight. I don't have much space for this. Yeah. If I scroll down, okay, that's nice. Let's see. So the column is the first die, the row is the second die, and inside the table are the sums. If it looks cyclic, that's because the integers under addition are a cyclic subgroup, or are a cyclic group, I should say. We can actually do this pretty quickly. Six, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Okay. So at this point, it just becomes a trivial counting exercise. Right, so 7 or 11, let's see. 1, 2, 3, 4, 5, 6, 7, 8. So 8/36 or 2/9. Here's a different color. 5 or 9. Let's see. 5, 1, 2, 3, 4, 5, 6, 7, 8. 8/36 again. Six or 8. 1. Oops. Yeah, the highlighter doesn't do it for me. Let's see, let's get some new colors. Nice. Use that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10/36. Or 5/18. And then finally 4 or 10. You could just subtract from 1 if you wanted to. That would be, nope. Let's go with that. Okay, 410. 1, 2, 3, 4, 5, 6, 636 or 1/6. Okay. Everybody okay with that?
Sorry, can you scroll up a bit again?
Yeah, sure. Yeah. Yeah, and to the question in the chat, how do we get 4/5, 10/11 to 2/3, right? So in lecture and workshop, we worked out these cases. So just to give you one example. So there was a case where we bet $11 and we got 10 back. So in other words, it was the case where we rolled a 6 first. We bet $11 and our expected payout was $10. So therefore, for every single dollar we bet, we got back 10/11ths of a dollar. Yeah. And all these are based on past cases that were worked out. And I think what we did was we worked out, for example, the case of like 9, and then Paul told us in the statement of the problem that's identical to the case of 5. So we only need to use 1. Yeah. So Paul gave us the cases in the statement of the problem. Does somebody want to plug this in and make sure it comes out to 488? Basically, all we're doing, right, is we're summing over payoffs times the probability. So we're going, product probability times payoff, and then we're summing the result. And that's our final answer. And this should be 488. Can anybody confirm that it comes out? Does anyone have it?
At least the probabilities all add up to 1. I was able to do that.
Yeah. Yeah, so that certainly would have to be the case, yeah. And I believe it is here, right? 3 9s, 5 9s. Yeah. Maybe while waiting for somebody to add it up, I'll verify that as a nice little sanity check. Let's see, so that's 5 9s, which is 10 18ths. So it's 15 18ths. Yeah, it's 1/6 is 3 18ths, so that adds up to 1. Yeah.
Yeah, it works out. I got it.
Okay. Awesome. Okay. Problem 4. Okay. As in workshop problem 1B, Amy, Bob, and Cal, that's 6 19ths. JS, 6 19ths for which? Oh. Oh, okay. For A and B? Oh, yeah. Oh, right. Those are the same probabilities. Okay. Well, let's talk about how to do them from scratch. So, as in workshop problem 1B, Amy, Bob, and Cal are assigned the leadership position on the committee by rolling a modified fair dice. 6 faces as usual, but 2 faces each with 0, 1, and 2. Okay, so we have a modified die. The phrasing here is kind of oxymoronic, isn't it? a modified fair die. If it's modified, oh, yeah, I guess it's fair. Okay, fine. We have a modified die. So it has 3 possible outcomes, 0, 1, 2, with probability 1/3, 1/3, 1/3. And they're going to roll in the order A, B, C, A, B, C, onward, 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 onward. Okay. So part A. By summing over the countably infinite set of events where Bob is the first to roll a 2, on rolls 1, 2, etc., find the probability that Bob is first to roll a 2. Okay, so what the probability that Bob wins, right? And basically what we're doing is we're using countable additivity. So we're saying the probability that Bob wins is the probability that Bob wins on the first, or he wins on the second, or he wins on the third, so forth and so on. Each of those is disjoint. So this is the probability that Bob wins on the first, plus the probability that Bob wins on the second, plus the probability that Bob wins on the third, and so forth. Everybody okay with the logic? Yes? No? Maybe?
Can you repeat that one more time?
Sure. So what we're basically doing is using countable additivity. So we're saying if Bob wins, he wins on either the first, or on his first turn, or he wins on the second turn, or his third, or so on and so on and so on. Each of these events is disjoint. So by countable additivity, this probability of this union of events is the sum of the probabilities. So this is the probability that Bob wins on his first turn, plus the probability wins on second turn, and so on and so on and so on. Does that make sense?
Yes.
Okay. So let's work at least a few of these out. I think in order to get the hang of the pattern, we should probably write 3 terms out. I think that's a pretty good rule of thumb. So with that in mind, and recalling that our order is A, B, C, A, B, C, A, B, C, what's the probability that Bob wins on his first turn?
What is that?
Oh, yeah.
2/3 times 1/3.
Okay, good. And what does the 2/3 represent?
The probability that Amy does not win.
Yep, exactly. Yeah, so this is Amy loses, which means that she rolled either a 0 or 1. And this is Bob gets his 1/3. Okay. And how about the probability that Bob wins on a second turn?
With 2/3 times 2/3 times 1/3.
Would it be 2/3 cubed?
No, not quite cubed. Everybody here is basically on the right track. So if Bob wins on his second turn, that means that he wins at this point, right? So in other words, that means that everybody who went before him must have failed, right? So that means that we must have had 4 failures here, right?
2/3 to the 4th then, times 1/3.
Exactly. And similar for his next turn, right? So in that was the case, there are 3 more failures. So what's the probability that he wins on his third turn?
Power 7 times 1/3.
So we can write this as a geometric series now. So this is the sum from k equals 0.
Sorry, is that a 2 over 3 to the 7th?
Yes.
Okay.
This is the sum of k equals 0 to infinity of 1/3 times 2/3 the sum power. And our exponents go 1, 4, 7, 10, 13, etc. So how might I describe that in terms of k?
K plus 3? No.
Sorry?
I was thinking K plus 3, that seemed to work for... Oh no, K plus 1.
Well, so let's put it this way. So every single time we're adding 3, right? So for every additional turn, we're adding 3k. Yes? But we started at 1. So in other words, it's 3k plus 1.
Yes.
And that sort of makes sense, right? So if k is 0, then the exponent's 1. That makes sense. K is 1, the exponent's 4. That makes sense, and so on. Okay, and JS is sort of ahead of us again. Yeah, so we want to turn this into a geometric series, but it's not quite there yet. So there are a couple things that we have to do to get this into the desired form. So what do we need to do? Okay, bring out a 2/3. So this is, I'll bring out the 1/3 as well. Bring out 1 factor of 2/3. So we have a sum from k equals 0 to infinity of 2/3 to the 3k. Right. So we have a 2/9 outside the sum. We have a sum from k equals 0 to infinity. 2/3 to 3k is exactly the same thing as 2/3 cubed to the k. Or in other words, eight 27ths to the k. And that is certainly less than 1 in absolute value. So this geometric series actually converges. Okay, so we'll use the geometric series. Oops. Okay, so you can treat the 2/9 as the first term if you want. I'm treating it as a constant factor. So we have 2/9 times, and what's the sum of a geometric series that starts at 1? Yeah. So in other words, if we had sum k equals 0 to infinity, a to the k plus 1, this would be a over 1 minus r. Yeah. In this case, our first term is 1 because we took out the factor of 2/9. This is 2/9 times 1 over 1 minus r, where r is 8 27ths. So this is 2/9 times 1 over 1 minus 8 over 27. And now we do some arithmetic. 2/9 times, let's see, 1 is 27 over 27, so our denominator is going to be 19 over 27. We flip that. We get 27 over 9. Cancel a factor of 9. And we get, definitely did something wrong. 19 is what I wanted to say here. 6/19. Okay. Jess, is that what you said you got? Okay. Okay. So that's part A. Everybody okay with that? Nobody's talking. Somebody should talk.
Yes.
Good. Okay. I was about to put a few people on the spot. Yeah. I was actually going to call up Farron, but I'm sure he's sleeping right now. Farron, are you awake? No, he's totally sleeping. Okay. Part B. Solve the problem in the same manner as the dueling problem done in the lecture. Let P denote the probability that Bob is the first to roll a 2. There are 2 ways for Bob to become chair. Either it happens on the first round or Bob is successful on a later round. Okay. So P is the probability that Bob wins. So all we're really doing is recursively defining this probability, right? So the probability that Bob wins is equal to the probability that Bob wins on turn 1, union with the probability that Bob wins on a later turn. And this is all equal to P. Now, what can I say about this union? For specifically these two, sorry.
Again, disjoint, so you can add them.
Yeah. By finding that additivity, you get P is the probability that Bob wins on turn 1, plus the probability that Bob wins on a later turn. Okay. So with that in mind, what's the probability that Bob wins in the first round? We worked it out earlier.
Two nines.
Okay. So we have P equals 2 9s. What's the probability that he wins on a later round? So we're calling again that our order is ABC, ABC, ABC.
So the other probability that we just calculated, that through the geometric series.
Which probability?
So the sum of that geometric series.
Well, so the sum of the geometric series is our little p.
Okay. Now we're doing the expected.
So let's put it this way. So the events are disjoint, right? So if Bob doesn't win on turn 1, then clearly these 3 are out of the picture, right? So what's the probability that nobody wins on the first round?
6 9 no 2 into 2 8 8 9
Or 8 27th?
Oh, so 27th, yes.
Yeah. Let's see. So that's okay. So okay. So he doesn't win on the first round, and then the experiment resets itself, right? And they all have to roll again. So going into the second round where Amy's starting and so forth, what's the probability that Bob wins? Yeah, exactly. Yeah, Mohit said it. So after the first round, the game resets itself, and its probability of winning is still P. Right. So in other words, probably that Bob wins on a later turn is 8 over 27s times P. Does that make sense to everybody?
Yes.
And now we do a little bit of alpha. What is a race? No race. Let's go to race. Oh my goodness. Okay, now it's erasing. Oh my goodness. It's about to cross it out. Okay. So let's see. Let's subtract 8/27s from both sides. So we get 19 over 27p equals 2/9. Let's multiply both sides by 27 over 19. This probably looks familiar at this point. Cancel. And we get 6/19.
Oh, hey, sorry, Mike. Could you scroll up one more time, please?
Yeah, sure.
Thanks.
Is everyone okay with this? Part C? Thank you, Mr. Sorry. Okay, part C. Using either technique, find the probability that Cal is first to roll a 2. Now you can check your answer since you have 3 probabilities that must sum to 1. Okay, so people are giving me the right answer, but we have to sort of work this out. So should we do this in a democratic way? So most people vote for the dueling technique, but we could also do a sum. So who votes for the dueling? Okay, who votes for the dueling technique? People are voting for the series. Oh my goodness. Okay, 2 votes for the series, 1 vote for dueling. 2 votes for dueling. 3 votes for dueling. Oh, 4 votes for dueling. Oh no, sorry, 3 votes for dueling. Okay. Yeah. I mean, let's put it this way. Both of them are pretty straightforward computations. Should we just do them both? Why don't we just do them both? Make everybody happy. Let's start with the dueling technique. Okay. So again, we have A, B, C, A, B, C. Probability that Cal wins. Let's see. So let's define the probability that Cal wins as alpha. Okay. So probability that Cal wins is the probability that Cal wins on the first round. Plus the probability Cal wins on a later round. Okay. What's the probability that Cal wins on round 1? So Cal would have to win at this slot. Okay. So 2/3, meaning that Amy and Bob both lose. Or rather, the 2/3 squared times the probability that he wins, which is 1/3. Okay. And what's the probability that Cal wins on a later round? So in other words, all three of these people have failed on the first round.
Same 2/3 to the power 3.
Times.
The same repeats.
Yeah. I'm actually really curious whether people are going to write alpha in their problem set. If you're LaTeX, you might opt for this little symbol. I think it's called like chi or something. I can't draw it, but it looks pretty cool. Feel free to use creative symbols. Okay, so let's see. So subtract 8/27's alpha from both sides. We get 19 over 27 alpha, which is equal to, let's see, 4/9. Sorry, 4/27s. Let's see. Oh, that's convenient. This is alpha equals 4/27s times 27 over 19. We get 4/19s. And to check our answer, we can say, well, we got 6/19 with the probability that Amy wins, and we got 9/19. Actually, sorry, we got 6/19 with the probability that Bob wins. We just computed that. And we got 9/19 with the probability that Amy wins from workshop. Those sum to 1. So clearly this answer is right. Provided that our other answers are right. Should we do the series? Who wants to do the series? JS? Okay, let's do the series. People keep entering, and I keep wondering if it's Joe. So I don't know if Joe is going to make an appearance. Okay. If somebody sees Joe, let me know. Oh. Review who didn't take 23A. Joe is my predecessor. He was the head TA in past semesters. And he might make an appearance tonight. Yeah. I think somebody is recording it, right? Or actually, I think a few people are trying to record it. So hopefully we will have a recording by the end of this, if not multiples, assuming that everything works as intended. Okay,
sorry, quick question.
Yeah.
It's my first meeting with you guys. So these recordings, where did you put them? So where can I get them?
So there is a course Slack channel. The link to it is on Canvas, and people would post the recording there.
Oh, yeah. Right. Thank you.
Mm-hmm. Let's see. So let's do the series. So we have ABC, ABC. Okay. So we're looking at the probability that Cal wins. So he either wins on his first turn, the second turn, or a later turn. So, JS, what's the probability that he wins in the first turn? Or anybody, but JS is making this. Yep. 2/3 times 2/3. Yeah, sure. So 2/3, Amy and Bob lose, and he wins. Okay. What's the probability that he wins on his second turn? etc. Is that a nice way to say the proof is trivial? Yeah. So we need 5 failures, so 2/3 to the 5th times a third. And basically the same thing where we're adding 3 additional failures each time. etc. I'm not sure how the TA would react to that. This is the sum from k equals 0 to infinity of 2/3. I'll pull the 1/3 out. 1/3 times 2/3 to the 2 plus 3n. We start with 2 and we're adding 3 each time. So let's pull out a factor of 4/9. Or I should say we'll pull out a factor of 2/3 squared. We'll do that in 2 steps. That leaves us with the sum of 2/3 to the power of 3n, but we'll pull the 3 inside. This is 8/27 to the n. This already looks familiar. Let's see. So this is 4/27. And this is 1 over 1 minus 8/27. So let's see. We'll have a 19/27 in our denominator. If we flip it, we get 4/27 times 27 over 19, and poof, 4/19. Yes, how does that look?
Wait, how is this any different from what we just did?
This is the alternate techniques. So here we're summing over a countable infinite number of outcomes. In the last one, we recursively define the probability.
Gotcha.
In my experience, people prefer the dueling strategy. But we had a nice split tonight. That's good. Okay. Oh, that's it for written problems. Do some more. Okay. So I'm going to pitch that we do our problem 1 at the end. And there are a couple of reasons for this. So 1, it's the toughest problem in the P set by far. And 2, there are a few people who have to leave now but are coming back later, and I want them to be able to see it. So it'll be okay if we do our problem 1 last? Okay. Mo, are you still here? Yes. Are we still here? Okay, I'm not sure if you can hear me. We do 4 now. Okay. Start with 4. Okay, so we'll go 4, 2, 3, 1. And so the funny thing is, I didn't even see. So page 32 in the outline is just blank. So I am kind of worried that people might just miss that and think there are only 2 R problems. Yeah, that's kind of concerning. Page 32 is a dud. Oh, and thankfully, for the sake of our MSA operative who's in attendance, I didn't divide by 0 a single time tonight. So that's good. I consider that a successful office hour. Oh, yeah, people are always muted, so I can't tell if anybody finds this funny. Like, you can either all be laughing or just rolling your eyes or just unfazed. I can never tell. Okay, good. Thank you. I'm not sure if it's sarcastic laughter, but I'll take it. Okay. I'll take your word for it. Yeah. So I'm gonna screen share. Although a note on this, when I have R up, I'm not able to see the chat. So people need to talk when we're doing R, or at the very least, somebody needs to talk and maybe be a messenger for people who aren't able to speak. Is anybody able to speak and willing to relay messages from the chat? Anyone? Bueller? Ah.
Sure, I'll do it.
Okay, thank you. Okay, let's do it. Okay. Problem 4. Well, as with all good things, let's start by clearing our console. I don't think I have anything in my console. Oh, I already cleared it. Okay, well, definitely cleared now.
You should clear the environment.
Yeah. Okay, problem 4. The file is Red Sox 2013 and Nats 2019. Extract the runs and runs against columns all into a single data vector with more than 600 entries. Okay. So let me ask, do you all have these files? I had to go digging for at least one of them.
We have them.
You have them? Okay, good. Good. Okay, so I'll just load them. Stocks. Okay. Okay, and let's take a look at both of them. Let's see. Okay. So seems like we have essentially the same columns. Both cases we have a runs and runs against column. So Paul says, extract the runs and runs against columns all into a single data vector with more than 600 entries. Okay. So let's extract R and RA columns from both data sets. So, okay, so let's see, let's call it capital X to make our lives a bit easier. We take a single vector. Doesn't really matter the order in which you do this. But I'll exhaust a data set first. So we take the runs from the Sox column, runs against from the Sox column, runs from the Sox data, and then finally runs against from the Nats data. Okay, and let's just check its length. It should be more than 600, as Paul told us. Okay, so it looks like we've accounted for everything. Everybody okay with that?
Yes.
Okay. Let's see. Part A. Make a bar plot of the number of runs scored by a team in a game. Okay, so there's one point that I want to make here. So you might be inclined to do something like this. Don't do this. We want to sort of itemize our bar plot by category. So what do we have to do first before we pass it to a bar plot?
Table?
Sorry? Table, yes. Table, yeah. We pass it there. I think why you make this thing look nice. So maybe we'll do that. So maybe we'll go, I don't know. XLab is number of runs. It is optional, but it might be nice to have a couple of these because in your term project you're going to be expected to kind of add these extra commands. So let's see. XLab is a number of runs Y lab is number of games. Color, I can pick something fancy here, I guess. Let's see. I'm gonna put in a bunch of random parameters and see if it works. Oh, not bad. Oh, that's right with that. Okay. So let's see. Okay, part B. If these data are modeled by a Poisson distribution, what is the parameter lambda? Okay. Anyone want to take a stab at that? What does lambda correspond?
Isn't it mean?
Mean, yes. Right. So, what's going on? Okay. So, if the data were modeled by a Poisson, lambda would be its mean. Okay. So we'll go mean of x, and we get 4.738235. Okay. Check whether the variance is close to lambda. So, might recall that for the case of a Poisson random variable, we have, let's see, so for a Poisson random variable, let's call it y, we have the expectation of y is the variance of y is lambda. So if the mean and the variance are very far off, that would imply that a Poisson model is not appropriate for the data. With that, check the variance. Okay. Those aren't even remotely close to each other. So very far off from the mean. Clearly, a Poisson is inappropriate. Is everyone okay with that conclusion?
Yeah.
Okay. And let's see. As is done with script 2D, topic 2 for home runs, carry out a chi-square test to see whether the number of runs per game is well modeled by a Poisson distribution. We should lump together games with large numbers of runs, so the expected number is at least 5. Okay. Let's see. So I have script 3D right here. Let's see. So there's a lot of code here, so maybe instead of copy and pasting it, maybe we can talk about what Paul did here. Okay. Let's see. So loads the data. So he's going to test whether this is Poisson. So he says if it's Poisson, it's going to have this parameter lambda. Its mean is going to be the parameter of the Poisson. So he computed one parameter from the data. This alone means that he has to subtract his degree of freedom. He made a table to get the distribution of runs, and what and the goal here ultimately is to figure out how to bin the data. So if each of these has, a reasonable number of counts, we could just have one bin corresponding to each, single value. But if any of them are particularly small, we'll want to pull some together. So that's what Paul's doing here. He's binning a few of these together and creating a new table. That gives him his observed data. Yeah, his home table is his observed. I guess you could pass this to the chi-square test as a table. We're going to pass it as a vector just to be extra careful, but I guess passing it as a table works. Can anybody confirm that's the case? Yeah, I guess they should give you the same outcome.
Sorry, can I ask a question before that? Because that's the part I was struggling with. This bar plot or histogram that you have on the screen right now, if you check, then the last number there is not 19, it's 20, because 19 is missing. So in all my calculations, basically what I was doing, I was just I was just converting it in a data frame, and I was adding one more row when I have 0 for 19 runs. Like, is it something that is expected us to do? Because it's just there were no observations where they had 19 runs. Because the reason I'm asking is because then when you compare it with a theoretical distribution, like for example what we'll do in equation 1, right?
Right.
Then a theoretical distribution has values for like 0 or or like missing values that you don't have. So essentially you need to plug it with zeros, right?
Right. Yeah. So that's a really good point. So say for the sake of argument that we wanted to consider a bin that has, I don't know, 30 in it, let's say, right? So in this case, because there obviously aren't any counts, our final bin would have to be the rest of the numbers to the upside that we couldn't have. So it might be, for example, just eyeballing this, it might be stuff that's bigger than 10, let's say, right? And for the case of comparing that to the expected distribution, that corresponding component of the vector would be the total number of games or total number of runs multiplied by the probability that something lands in that bin. So the probability that's greater than or equal to 10. So in other words, we account for missing data by binning it together with observations that we do have.
Yeah, I understand, because we're essentially like summing up all the tails, so it doesn't matter if we have missing data there or not. But I was more concerned about like equation 1, because there we have pretty much the same situation when there is like a bunch of missing numbers.
So making the bar plot, you mean?
Well, both making a bar plot and doing a chi-square test. But again, like I don't want to jump like too ahead, because you said that we're going to discuss question 1 sometime later, right? It's just occurred to me that.
Okay, sorry. I thought you meant 4A rather than question 1. Right, okay.
No, it just relates to that, because here I understand that it's not a big deal because we're just summing up all the tails, so whether we have missing numbers or not, it's not a big deal. But in question 1, it might become.
Right. Yeah, so let's see. So in question 1, so the 0 case won't be an issue because of the way in which R parameterizes geometric. So R doesn't count the success for a geometric random variable. So when we say there's one game between wins, and R calls that 0. So on the bottom side, we're going to be okay. If there's anything missed, then we'll just bin it together. So for example, if there are no observations for 4, we might say one bin is 3 and 4, let's say. And then our last bin will be greater than or equal to something.
Okay, all right. Yeah, but again, like, sorry, I didn't mean to disturb you because we're going to discuss question 1 later, right?
No, asking any questions is totally welcome. That was a good question. Certainly. Yeah, we'll go through problem 1 in depth. Okay, let's see. So, so the key with this expected column is, with this expected vector, is that once we compute it, its sum should be equal to 162. Should be equal to the total number of observations. Right. And basically what we're doing is saying, okay, take the probability, so take the total number of observations and consider the probability that an observation lands in some bin. That component of the vector will be the total number of observations times the probability that something lands in that bin. The probabilities provide a weight, in other words. Think of 162 as a pie, and we're splitting it into, we're sort of just dividing up the pie amongst the components of this vector. Then we get the chi-square statistic. We pass it to the p-chi function. This is, if we didn't have this lower dot tail equals false argument, this would be a cumulative distribution function. So for some x, it'd be the probability that the random variable is less than or equal to that x. Because we specified lower dot tail equals false, it's a survival function. So the probability that the random variable is greater than some x. With 3 degrees of freedom, I think Paul has 5 categories here. Oh no, he has 6 categories. 6 categories? No, okay. Oh, 5 categories. Okay, because he's pulling this together into his last bin, right? So yeah, so we have 5 categories, and so we estimated one parameter from the data, lambda, and we made our expected number of observations equal to our total number of observed data. Also sacrifice degree of freedom. But we had to sacrifice 2 degrees of freedom. So we ended up with 5 minus 2 equals 3 degrees of freedom. We got a p-value. And it seems in this case that Paul got a large p-value. So basically what that p-value says is the probability that we would observe a test statistic as extreme as the one that we got. So if that's a really high probability, then that would imply evidence that our data came from the intended distribution. If not, if it's really rare, then that's evidence against the null hypothesis. Okay. First of all, is everybody okay with which Paul did in script 3D?
Yes.
Okay. So let's do it then. Okay. Let's see. So one of the very first things that Paul did was load a table. So let's do that. We're not creating the expected counts just yet. We just want to check the distribution. Okay, let's see. So all of these lower numbers look totally fine. These are nice numbers. 7 counts, that's fine. Everything from 14 onward, I mean, 50, except for maybe the 15, is pretty small. So, I mean, there really is no wrong way to do this, provided that each of your counts is at least 5. For simplicity, I'm going to pull together everything that's greater than or equal to 14 into one bin. Everybody okay with that?
Yeah, sounds okay.
We'll say we need to have at least 5 in order to run the chi-square test. Let's pull together data greater than or equal to 14 to one bin. So our bins are, this is optional, but 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and greater than or equal to 14. Okay. So let's create an observed vector. So we have 15 bins in total.
Sorry, how did we decide that we need at least 5?
So that's a general rule of thumb for the chi-square test. I'm not sure if I would say that that's in the literature. I think I'd be willing to bet that the literature probably has a number higher than 5. I think 5 is our compromise for this class.
That's what Paul also mentioned in the lecture, that don't ask me what 5 it is. So.
Yeah. So in our case, we're fine with 5. I mean, ideally we would have more. But yeah. Okay, so we'll say so we have 15 bins. So let's create an observed vector. A numeric 15 is just an empty vector with 15 entries. And for the first 14 bins, so from 0 all the way to 13, it's just equal to the corresponding column of the table, right? So for the first 14 bins, we should loop through the table. Is everybody with me? So say for I in 1, 2, 14. And the index starts in 1 in R. So this is index 1, index 2, 3, 4, and so forth. So we'll say the ith component of observed is equal to table X, ith component. We can line these up to make sure that it worked appropriately. Yeah, so 42, 59, 84, 96. And the only thing that we haven't yet done is this final entry, right? Because we haven't done anything with the 15th entry yet, but we're going to take care of that in a second. Sound good? Anyone? People need to talk. It's lonely.
Yeah, so sorry I missed that. How come I was distracted for a moment. Why are we seeing a 0 at the end?
So when we first ran this numeric command, we got an empty vector with just zeros.
Okay.
So we dealt with the first 14 entries. We haven't done anything with the 15th entry yet. We have to take care of that right now.
Fine.
Because you couldn't just use a loop for it. Yeah?
Got it.
Okay. So now we'll say deal with the 15th bin. So what we have to do is say, okay, 15th entry. I want to sum. Let's see. I want to sum from 14 through 20. So this is column 15, 16, 17, 18, 19, 20. Yeah, that works out because we skipped 19. Yeah. And maybe to answer another question on this is actually a really, really good point. The bin itself is all positive integers greater than or equal to 14. So technically, 19 would be in this bin. Like in the theoretical bin, 19 is included. We just have 0 observations for it. Also, 21, 22, and so forth are in this bin. So we can say sum table X index 15 to 20. Okay. And we could either just kind of sum these by inspection. Let's see, 9, 10, 11, 12, 13, 14. Okay. Or we could say, well, we have 680 data in total, right? We took the length of our vector X. So because we've accounted for all of our runs, if we were to sum across the observed vector, we should also get 680, right? I mean, we've accounted for every single run. Yes. We get summing across the vector. So observed. We do. Hey. Okay. So there's the observed vector. Now we need to deal with the expected vector. And use a loop. We can actually do this in one shot, because multiplication in R is vectorized, thankfully. So, okay. Create expected vector. Okay. So it's usually the same deal for this. So, you know what? I'll make our life a bit easier. This is me being lazy. Let's save the length to an object. So I don't have to write length X. So the length is capital N. Okay, so total number of observations N times, now we're going to multiply by the vector of probabilities. So the probability that our bins, recall, were, first we just have these singleton values. So it's the positive integers from 0 to 13 as well. So our vector is going to be T puts on 0 to 13, and we have a lambda. What this will do is it'll say the first component multiply capital N by the Poisson probability of 0, second component capital N by the Poisson probability of 1, third component N times the Poisson probability of 3, and so forth. Sorry. Third component would be N times the Poisson probability of 2, because this goes 0, 1, 2. So this deal with the first 14 bins. But now we have to deal with the final bin. And the final bin is greater than or equal to 14, right? But the Poisson distribution takes on integer values. So Poisson takes on integer values. The probability that x is greater than or equal to 14 is the same thing as the probability that x is strictly greater than 13. So we can use the Poisson function. PPOS, give me the survival probability of 13 lambda, and we specify lower dot tail equals false. And if you want to send a check here, do these probabilities sum to 1. I mean, it's equivalent to summing the expectation and getting n, but we'll do both for fun. Sum of d Poisson short of 13 lambda plus p Poisson 13 lambda lower dot tail equals false. They do, and we can say, does the expected vector sum to 1, or I should say, do the components of the expected vector sum to 1? Sum expected, or not 1, capital N, or 680. They do. Okay. Okay, so final question. How many degrees of freedom do we have? Anybody want to take a shot?
Sorry, Michael, could you explain again what degrees of freedom are?
Sure.
Okay, cool.
So, yeah, so here I think is the best way to think about it. So let's say that we have 5 numbers, A, B, C, D, E, and we're given that their average is 15, or you know what, let's make this easy. Their average is 10, right? So that means that their sum has to be 50, right? So for the first 4 values, we can make these anything we want. So I don't know, I can make this like 20, 23, negative 40, negative 10, whatever. But if after I pick these 4 values, my E is fixed because I need these to sum to 50, right?
Right.
So I've lost 1 degree of freedom by fixing this average at 10.
You would have 4 degrees of freedom.
Exactly.
Okay, cool.
Does that make sense to everybody? I found that a lot of cases, a lot of stats courses don't explain degrees of freedom, which is kind of upsetting. But hopefully that did it justice.
I guess I'm still a bit confused how that applies to what we're doing here. Just translating it from, like, I get what you're saying with the metaphor here, or
yeah,
what you want to call it, but into distribution.
Right. So basic idea is that we're trying to look at sort of a relevant chi-square distribution, and we're trying to see how extreme our test statistic is on the pertinent chi-square distribution. And so the only parameter of a chi-square distribution is degrees of freedom. And we haven't really gotten into this. We might later in the course. A chi-square random variable is a sum of some number of squares of standard or normal random variables. So and the number of independent standard normal random variables we're summing is equal to the number of degrees of freedom. So that just specifies the chi-square distribution that we're going to look at. Sound good? Shall we keep going?
Yes.
Okay. Hopefully that made sense. Okay. So how many degrees of freedom do we have?
So the categories minus 2.
Okay. So yeah, exactly. So we lost 1 degree of freedom when we fixed our expected value at n, because our expected terms had to sum to 1, and we computed lambda from the data. So we lost another degree of freedom there. So our degrees of freedom is 13. We can say we set the expected total equal to the actual total, n. We computed lambda from the data of 15 categories, hence 15 minus 2. Okay, now we get our p-value. So we use the survival function for the chi-square distribution. So we give it, oh, we didn't compute a chi-square statistic, did we? Huh, let's go do that. Compute chi-square statistic. Okay. I mean, the formula for this isn't too complicated, but we probably want to go and grab Paul's function for this. It's pretty convenient, so let's see. Where is Paul's function? What is it? Oh, it's right there, I think. Yes, okay. So say compute chi-square statistic, borrow Paul's function. You don't have to. It's kind of convenient. Okay. And then compute statistic. So let's call it CHISQ, or lowercase. The function, I have to be careful with cases here. So let's see, we pass it our observed vector and our expected vector. And we get, that is really, really large. That is like abnormally large. So you already tell we're going to be failing to reject the null. Or sorry, we're going to be rejecting the null, which makes sense because our variance and mean didn't line up. In other words, this is really, really extreme. Compute p-value. This is going to be like ridiculously close to 0. So df's and lower dot tail is false. Yeah. Look at that. 10 to the negative 227. Oh my goodness. I can't even write that out. That's how bad that is. This is absurdly close to 0. That is, and let's interpret it at least once tonight. So that is the probability of observing a test statistic. This is the case for a chi-square goodness of fit test. So observing not a test of independence as we were doing in past weeks. So the probability of observing a test statistic that is as extreme from the relevant chi-square distribution with 13 degrees of freedom as we computed is essentially 0. This gives us enough evidence to reject the null hypothesis that the data came from a Poisson distribution with parameter lambda. Sound good?
Yes.
Okay. Okay, so that's problem 4. Jump back to 2.
Yes.
Yeah, 2 and 3 are a lot of fun, at least I think. So we'll have some fun doing 2 and 3, and then we'll get to 1, and we'll probably have a group therapy session, but we'll get through it. Okay, the command p equals whole bunch of probabilities, generates vector probabilities for random variable x that can have any value from 1 to 1,000. Okay, so I have to admit something. Every single time I run this line of code, I mistype it. So I'm just going to copy and paste from Paul's outline. So take vector of probabilities from Paul's problem. Okay. And normally I would check these sum to 1, but that's actually the first part of part A. So we can just do that in part A. Let's see. Does this vector of probabilities, or say, do these probabilities sum to 1? Sum to, so we go sum p. They do. That's good. Let's see, compute the expected value of x and the expected value of x squared. So our outcomes are values 1 to 1,000. Okay, so how do we get the expectation?
Sum of probability times the value.
We can do the mean, right?
So if we were to just take the mean of, say, the vector 1 to 1,000, that would assume equal probabilities for each of these values.
Yeah, but you can multiply it by your vector of probabilities.
Let's see. Wait.
No, but probably
That
the
goes a
other way.
vectorized.
Yeah.
No, it should be one number, so you need to put parentheses, I guess.
So p itself is a vector, right?
Yeah.
Whereas mean is a scalar. So all we're doing here is we're scaling a vector. But
No, I mean you need to put parentheses around this. So you multiply this 1 to 1,000 by p, and then you take a mean of it, right?
Okay, let's see. So put parentheses around there.
No. Parentheses after p.
After p.
Okay, so put parentheses after.
That's the same as, each probability now being multiplied by each value, because we are doing one at a time and then taking a mean of that.
Yes. Yeah, but again, the first parenthesis should be after mean.
After mean, okay.
Yep.
Okay.
No, that doesn't change anything. No.
No,
Okay.
don't change. Yeah.
Okay.
No.
Where your cursor is, put parentheses, just closing parentheses. Then
Okay.
go left 1, 2, 3, 4 times and delete one parenthesis. Yeah.
Okay.
Yeah.
That's it.
Right.
Okay, let's go with this. I don't believe this is right.
Yeah, we don't need the mean, it seems, because we just need the multiple that you're doing, I guess. No, not the mean, because each value multiplied by each probability and keep adding them. The sum is probably what you need to do, not the mean.
Yeah.
The mean changes to sum, and it's the same formula.
Right.
That makes sense.
Yeah. So what we're basically trying to do is, so in a discrete case, we summed over outcomes. So we summed a whole bunch of products. No, we want 1 times the probability of 1, 2 times the probability of 2, 3 times the probability of 3, etc., all the way through 1,000. And we can kind of do that in a vectorized way. So this is going to be. So in other words, what we were just doing is we computed a single value and we multiplied all the probabilities by that. But our random variables can take on 1,000 values. So we want 1 over 1,000 times p, and we want to sum over all these probabilities. Okay. So we get 5.15, 8213. Okay. One second. let's see, and Paul wants the second moment. So here, pick the value of x squared. Okay. What do we do now? So we literally square each of these outcomes, right? Okay, so let's see. Confirm that about half of the sum, or the expected value of x squared, comes from the tiny probability for x equals 1,000. Okay. So find contribution of the small probability for x equals 1,000. How do I do that?
The 2,000 into 2,000th element of p, I guess.
Sorry, say it again.
That's 1,000 into the 1,000th element of p.
Yeah. So we're gonna take the outcome of 1,000, scale it by its probability. So this itself is the contribution. And then we can divide this by the second moment. What just happened? Something happened here.
So if you're doing squared, then if you're doing x squared, then probably we need twice of the square of that.
Ah, right. Okay. Yes. So that should be squared.
No.
Right, good. Okay, there we go. Little over 50% as desired. Okay, good, thank you. Okay. Part B. Okay. Display a histogram of 10,000 samples from this distribution. We need to use breaks equals 100 as a second argument to the histogram function in order to see what is happening. Okay. Thankfully, Paul gives us some nice code for finding samples. So let me grab Paul's code. We'll basically use this. Okay, let's see. So let's call our samples, I don't know, y. So we use the sample function. We're interested in the numbers from 1 to 10,000. Is that right? Oh, no, sorry, 1 to 1,000.